Okay, next let's start with the element 2. So element 2, which is having two nodes, 2 and 3. So here I can go for the procedure, either I can pick 2 to 3 or 3 to 2. So both are uh, can be considered. Okay, and later on the length of the element, here your simplification factor is, since it is completely vertical, I can directly pick that element. Length of the element is 30 mm. Otherwise I should calculate that. Okay, length of the element as 30. And let's calculate the what we call the direction cosine L. So if you pick the direction cosine L for this one, so there is all these factors. Yeah. Sorry. So L for the element 2, so L is equal to, yeah, here it is there, L is equal to x3 minus x2, because x final minus x initial, x final is x3, y final x initial is x2. Okay, so that is x3 minus x2 divided by LE, so that it becomes 40 minus 40 divided by length of the element, that is 0. Since it becomes 0, the numerator, so L also becomes 0. And later on, to calculate M, so what we should do is y3 minus y2 divided by length of the element. So y3 is, from this table, y3 is 30, and therefore 30 minus 0, and y2 is 0. Okay, so that it becomes 30 minus 0 divided by 30, that equal to 1. Okay, in the same way, the next part is, that is the Young's modulus. Okay, as I said, so Young's modulus as well as cross sectional area, both are same for the element 2 also. And let us look into the global connectivity. So global connectivity for the node 2, sorry, element 2 is, since it starts from node 2 to node 3, so that global connectivity is Q3, Q4, Q5, Q6. Okay, so Q3, Q4, Q3, Q4, Q5 and Q6. Okay, so like this, so you have to do this. Why it starts from Q3, Q4? Because initial node is 2, that's why. Okay, okay, so let's go for element 3. So element 3, so this one, the mid one. So here you need to go for the initial node and final node. So where I can go for either picking node 1, initial node as node 1 and final node as node 3, or else initial node as node 3 and final node as node 1. Okay, let's go for 3 to 1 itself. So 3 to 1, and thereafter I should calculate what we call the length of the element. So here I should prefer what is the equation. This equation I need to use. Okay, so LE is equal to x final minus x initial whole square plus y final minus y initial whole square. Okay, in all comes in the square root. Okay, so now let's go for this one, x final minus x initial, that is x1 minus x3. So x1 minus x3 is 0 minus 40. So I am going to write down that here for the element 3. So length of the element, so that LE, okay, length of the element, square root of, okay, x final, that is x1 value is 0. So 0 minus x initial, that is 3, that is 40. So 40 whole square plus y1 minus y3. So y1 is 0 and y3 is 30. So likewise, if you do, then it becomes 50. Okay, so 50 mm. And let us look into these quantities direction cosines L and M. So here element 3. So final node is 1, initial node is 3. Therefore the equation becomes x1 minus x3 divided by length of element is 0 minus 40 divided by 50, and the value becomes minus 0.8, and M is equal to y1 minus, that is y final minus y initial, that is y1 minus y3 divided by length of element, 0 minus 30 divided by 50, that equal to minus 0.6. Okay. So these two values you enter here. Young's modulus, area, both are same for this element also. And coming to this global connectivity, since it starts from 3 to 1, okay, 3 to 1, so what I should do is, I should consider the initial node first, that is Q5, Q6 and Q1, Q2. So you have to write down this Q5, Q6 and later on Q1, Q2. Okay. So if I choose 1 to 3, then it becomes swap. Okay, Q1, Q2, Q5, Q6. Okay, like that. So you should remember that this factor affects global connectivity, both initial node and final node. Yeah. Element 4, let us consider. Okay, element 4, that is this one, which is having, I can going to pick this initial node as 3, final node as 4. Let us calculate the length of the element. Again, it is simply it is horizontal. I will directly pick 40 mm set as length of the element, or else I should calculate that. Next, direction cosines L and M. So for the direction cosines L and M, let us have a look into this equations. X final is 4 and x initial is 3, that is x4 minus x3 divided by LE, that equal to 0 minus 40 divided by 40, so that it becomes minus 1. So for M, y4 minus y3, so y4 minus y3, so y4 is 40 and y4 is 30 and y3 is also 30, so 30 minus 30 divided by 40, so that it becomes 0. So enter those values. One is minus 1, 0, and in Young's modulus it is same for what we call element 4, cross sectional area, that is also same. And coming to the global connectivity, since I pick 3 as initial node, 4 as final node, so from where I should start? From Q5. Okay, that is Q5, Q6, later on Q7 and then Q8. Okay, so like this I have to refer global connectivity. So once this table is finished, let us go for calculation of stiffness matrix. Okay, so element stiffness matrix, that is, we know that AE by L, L square ML M L square, which is a 4 cross 4 matrix. So this one I need to pick, so you have to remember this. Let us go for the element stiffness matrix of the element 1. Okay, all these quantities what I have calculated previously, I am going to use it right now. Okay, so element stiffness matrix, so area of the element 1, Young's modulus of the element 1 and length of the element 1. Let us look into this table. So area of the element, it is 100 mm square. Young's modulus, it is 2 into 10 raised to 5. Length of the element as 40. Okay, so all these values you enter here, multiply by the matrix. So matrix should consisting of L and M values. So L value is 1 for the element 1 and M value is 0. Okay, so you enter all those. So if you enter, then it becomes 1 0 minus 1 0 0 0 0 minus 1 0 1 0 0 0 0 0. Okay, so once this is done, so you simplify this number and multiply that into the matrix. So here it becomes, so all those quantities will nullify, okay, which results into simple this matrix. Okay, so here the next thing is global connectivity. So you have to do this. How will you do that? By referring this table itself. So it starts from 1, 2, 3, 4. So 1, 2, 3, 4. Mention the particular rows and columns as 1, 2, 3, 4. Okay, and maintain the same uh, powers outside the matrix. Okay, so once this is done, let us move on to the element 2. So element 2 area is same, Young's modulus is same, and length of the area element 2 is 30. So enter that and multiply by, so L and M values. So L and M values, let us look into this. L value is 0, M value is 1. Okay, so enter those quantities, and so that I am going to get this table, and once you get this, simplify this number. Okay, 2 into 10 raised to 5 divided by 30. Okay, and you are going to get some number, and that number you need to multiply into the matrix. You have to multiply that into the matrix, only the number, and maintain the same power. So since previously I mentioned 10 raised to 5, so here also I am going to maintain the same power. Once this matrix calculation is over, you need to strictly how to do the global connectivity actions. Okay, for that you again come back to this and look into this. So it starts from 3, 4, 5, 6. So that's why I will mention each rows and columns as 3, 4, 5, 6. 3, 4, 5, 6. Okay, so once this is done, so the next I am quickly going to the element 3. Element 3, 100 into 10 2 into 10 raised to 5 divided by 50 divided by 50. So Young's modulus array is same, and L value is minus 0.8 and M value is 0.6. Okay, so L value, M value you have to enter. Okay, do the squaring and multiply L M quantities, so that I am going to get this number. So this is very carefully how to do that. And once you did that, the next part is multiply the numbers what you are going to get from the constants, multiply that into the matrix. Once you multiply that, maintain the same power, write down the number. Okay, so here also global connectivity should be mentioned. So as I said, for element 3, it starts from Q5, Q6, Q1, Q2, 5, 6, 1, 2. Okay, 5, 6, 1, 2. So once you did this, the next part is for the element 4. It is 100 into 2 into 10 raised to 5 divided by 40 only, multiply by the LM quantity. So LM quantity is minus 1, 1 for the element 4. Okay, so once you find out that, you just substitute and multiply those numbers, simplify it, and you are going to get this matrix. So here also global connectivity should be mentioned, and that you should take it from the previous table. Okay, so once this is finished, I should go for global stiffness matrix, which is nothing but summation of all stiffness matrix. Okay, that's what it is asked in the problem. Okay, while doing this, you should be very careful. Since we are having 8 degrees of freedom, so the global stiffness matrix is also having 8 cross 8 matrix. Okay, 8 cross 8 matrix. So like this. So first you write down the 8 cross 8 matrix, and later on from all stiffness matrix, before that you mention the each rows with the global degrees of freedom 1, 2, 3, 4, 5, 6, 7, 8. In each column has 1, 2, 3, 4, 5, 6, 7, 8. Okay, once this is done, you have to refer the individual element stiffness matrix, and for each coefficients, that is the A11, A12 like that. So here 11 which is having 1 number 1, and we don't find any 1 connectivity from element 2. For element 3 I am having 1 connectivity, that is 2.56. Okay, so that it becomes 1 plus 1 plus 2.56. Okay, so like that you have to write down that number. Okay, next 2 connectivity. So what is that? 2 1 connectivity. So 2 1 connectivity is 0 here, and 2 1 connectivity I am not finding in element 2, and in element 3 I am having 2 1 connectivity, that is 1.92. So that 0 plus 1.92. Okay, like that you have to do all the questions considering from each matrix, element stiffness matrix. Okay, so once you did that, this portion is actually a time consuming. So what you can do is, since element stiffness matrix as well as global stiffness matrix is having the property of symmetry, you can fill only the upper diagonal quantities and you can copy that to the lower diagonal values. So if you are doing in this way, this should be double checked. Okay, all these values should be double checked. Okay, once global stiffness matrix is finished, next part is global displacement vector. So as I said, uh, here we are having what we call 8 degrees of freedom. So global displacement vector, which is consisting of 8 quantities Q1, Q2, Q3, Q4, Q5, Q6, Q7, Q8. Since it is a column vector, so you need to represent that in the, either you can go for transpose of that. Okay, for easy representation. Next, global force vector. So this you will get it from that figure itself, the FEA model. So it starts from F1 and end to F8. Okay. So write down all those force values, and let us look into the external forces that is actually acting here. Okay. So let us have a look into this FEA model. At node 1 we don't have any external forces. Okay. So F1 is 0, F2 is 0. At node 2 we are having one force magnitude, that is 20,000 Newton, and that is F3, and that is along the direction of X. Along the direction of X. So that plus 20,000 Newton, that is F3. Okay, and F4 we don't have any F4. And coming to node 3, we don't have any F5 quantities, and we are having F6 quantity, that is 25,000, but it is against to the axis system, that is F6 is equal to minus 25,000. Okay, coming to the node 4, we are having no external force, F7 and F8. So only two quantities, F3 and F6. F3 is plus 20,000 Newton. F6 is minus 25,000 Newton. Okay, so write down all those quantities here and makes all other as 0. So once this is finished, next part is equilibrium equation. So you have to write down the equilibrium equation, that is in terms of KQ equal to F. So all the global values or global matrix what you calculated previously, you write down in this way. So once you write down that, you should go for applying boundary conditions. To apply the boundary conditions, I am going to adopt the what we call elimination method. So in order to have these boundary conditions, let us look into the quantities of displacement values. From the figure, node 1 is completely fixed, therefore Q1 equal to Q2 equal to 0, and node 2 since it is a roller sequence, it can be easily moving in x direction, but it is unable to move in y direction. That is, Q3 is not equal to 0, but Q4 equal to 0. Okay, Q3 is having some magnitude. So Q1 and Q2 are 0, Q4 is 0. This is not at all restricted, that is should have some values. And node 4 is also completely fixed. Therefore Q7, Q8 is fixed. So 1, 2, 3, 4, 5. 5 values I should eliminate from the given matrix. Okay, so that is Q1 should be 0. So eliminate first column, first row, and later on second column, second row. After that, so Q4 you have to eliminate, and the fourth row and fourth column. Later on Q7 and Q8. Q7, Q8. That is yeah. So once you eliminated that, I am going to get 3 values only. That is 5, 0, 0, 0, 7.56, 1.92, 0, 1.92, 8.1 from the stiffness matrix, and from displacement, that is Q3, Q5, Q6, and from force quantities it is 20,000, 0, minus 25,000. So it will be a 3 cross 3 matrix. So write down that. Don't forget to have 10 raised to 5. Okay, and later on solve this matrix. Okay, so once you solve that, I am going to get Q3 equal to 0.04, Q5 equal to 0.0083 mm, and Q6 is equal to minus 0.0328. So better you cross check that while you are calculating those quantities. Once you did this, the next part is the nodal displacement vector. You simply write down in that matrix or these values into the global values, global displacement vector. It's later on stresses in the each element that you can calculate, but using the same equation E by L minus M Lm, and for this you have to refer the global connectivity table. Okay, so since it starts from node 1 to 2, at Q1, Q2, Q3, Q4. Okay, and first element, let's pick Q sigma 1 is equal to 2 into 10 raised to 5 divided by length of the element is 40, and write down Lm values from the table. Okay, from the table of element 1. Okay, that is this table. From this table, what is the value of L, what is the value of M for the element 1. Okay, that one you have to write down here. So you should be careful while doing all these calculations. Yeah, once you did that, next to substitution of the global displacement values. So Q1 is 0, we know that Q2 is 0, but Q3 is having some value, that is 0.04, and Q4 is having 0. So if you do that, I am going to get sigma 1 is equal to 200 Newton per mm square. Okay, next for the second element, and that is E by L. So Young's modulus is 20 10 raised to 5 divided by 30. That you need to pick from the element table. Okay, and pick the L and M values from the element table. So L value for the element 2 is 0 and M value is 1. So write down that L value and M value and mention displacements. Okay, this displacement, okay, how you are going to take by using element table itself, that is global connectivity. For element 2, it starts from Q3 to Q6. Okay, so Q3, Q4, Q6, Q5, Q6. Better you should have a look into this. Q3, Q4, Q5, Q6. Okay, so write down that all the displacement values and calculate the stresses. Sigma 2 equal to minus 218.93 Newton per mm square. Third element, do the same procedure and I'm going to get it as minus 52.112. And for the element 4, 7 Newton per mm square. So once you did this, the procedure to calculate the stresses and stresses are over. Okay, I hope everyone will follow this problem. Okay, and practice a few more problems for your better understanding and ask me for any queries. Okay, thank you everyone for your patience listening.